Hi everybody, in this video we are going to be talking about one of the applications of your fundamental trig identities that we learned in the last section, and that is verifying new trig identities, more complicated ones. So we're going to do a few examples of this. You should think of these examples as just models for how you might go through this process, but every time that you verify a trig identity, it's kind of like a brand new puzzle, and you just need to think really hard about it and think of your fundamental trig identities as your tools. I'll give you some strategies, but there's no set fire way to get it right every time. It's more of a fun challenge. So let's look through some examples. One of the strategies that you might use when verifying a trig identity, like this one, is to work with one side at a time, and generally we start with the more complicated side. Then we're going to use our fundamental identities to simplify it more, and we might use strategies such as factoring, adding fractions, and others. If these first three things completely fail, then you can always convert everything to sine and cosine. That might make things a little bit easier. We'll do an example like that. But most importantly, you just need to try something. Anything. Just change it a little bit and maybe something will stand out to you that will actually work. So let's look at this example. My first strategy says to start with the more complicated side. To me, this side looks more complicated, and so let's start out by trying to simplify that. The first thing I notice is that the numerator looks like part of my Pythagorean identity. Oftentimes when you see a squared, you should be thinking Pythagorean identity. So I'm going to use that first. This becomes tan squared of theta on the top, and the bottom is the same. And for now, I want you to get into the practice of writing the reason why something is true. So this is by the Pythagorean identity. Now my next step is I need to get some cancellation on the top and bottom. So maybe I'm going to convert things to sines and cosines by using the quotient identity on the top and the reciprocal identity on bottom. The quotient identity says that tan squared is sine squared theta over cosine squared theta. And the reciprocal identity says that secant squared is 1 over cosine squared theta. So again, this is because of quotient identity, and this one is because of the reciprocal identity. So here I've converted to sines and cosines because it allows me to get some cancellation. So the way that I divide by a fraction is I multiply by the reciprocal. So here I have sine squared theta over cosine squared theta times cosine squared theta over 1. And the cosine on top cancels with cosine on bottom, so I end up with just sine squared theta, which is what I wanted to get. So now I am done. So this step was just simplify. Okay, let's do a slightly more complicated example now. I want to verify this identity, 1 over cos x plus 1 over cos x minus 1 equals minus 2 cosecant x cotan x. So to me, this side looks more complicated. So let's start out trying to adjust this side and make it look like this one. Now, one of my strategies here was adding expressions. So when I have two different expressions, but I'm supposed to end up with just one, I better get a common denominator so that I can combine these. So my first step towards getting a common denominator is I notice that if I multiply this one on top and bottom by cos x minus 1, and this one on top and bottom by cos x plus 1, I'll have the denominator cos x plus 1 times cos x minus 1. So let's write that down. Cos x minus 1 over cos x minus 1. So this is just a clever way of multiplying this fraction by 1. And I do the same thing to this fraction. So now, when I simplify these two, on top here, I'll have cos x minus 1 over cos x minus 1 times cos x plus 1 plus, on this one, I have cos x plus 1 on top over the same denominator and so all I did here was get a common denominator. Now I can add these two numerators because I have the same denominator. So I get 2 cos x because I combine these two, and minus 1 and plus 1 cancel. So my numerator is just 2 times cosine x. My denominator, notice that when I multiply these together, I have to FOIL. So first is cos squared x, outer is cos x, inner is minus cos x, and last is minus 1. So when I multiply those terms together, I get cos squared minus 1. So that's my denominator. And so what I used here is just simplify / add fractions. Now notice, if you look at cos squared x minus 1, this is the same as minus cos squared x plus 1, which by the Pythagorean identity is minus sine squared x. Right? Yes, okay. So I get here minus, or let's say 2 cos x over minus sine squared x, which I could write as 2 over minus sine squared, or minus sine x, times cos x over sine x. The only reason I did this is because I know I'm supposed to have two different trig functions at the end. So this step was by Pythagorean identity. And finally, if I look at this term, this is minus 2 cosecant x, and this term is cotan x. The first one is by reciprocal identity, and this is by quotient identity. And that's what I wanted. But just one quick thing to point out. At this stage, you could have also written it as 2 cos x times minus cosecant squared x, because the 1 over sine squared x would be cosecant squared x. The only reason I didn't write it this way is because I was trying to get it to look like this. So instead of getting rid of 1 over sine as cosecant, I split it into two different terms, so I could get just one copy of cosecant instead of cosecant squared, and I could get a cotan also. So sometimes you need to be a little bit clever in the way that you break up the fraction. So let's see a third example. This one is looking rather complicated, and there's no obvious connections between all of these different things. I would say this side is the more complicated one because it's two different terms, so we'll start here. And maybe I don't know what to do. So I can always switch to sines and cosines. So cosecant we know is the same as 1 over sine x, and then I'll have minus sine x. And that's just by the reciprocal identity. Now I need to combine these two terms, so I'll get a common denominator. So I'll have sine x over, or let's see, my common denominator is going to be sine x, so the first term I'll leave the same. To get the second term to have denominator sine x, I have to multiply top and bottom by sine x. I get sine squared x on top and sine x on bottom. So here I'm just getting common denominator. Now notice that the top is 1 minus sine squared x. So by the Pythagorean identity, that's cosine squared x on top over sine x. And now notice that we're trying to get this to look like cosine x times cotan x. So I need to separate this into the product of two terms. I have two copies of cosine, so maybe my first term will be cosine x over sine x, and the second one will be cosine x over 1. So I haven't really done anything, I just split up that squared into two different copies of cosine so I can get two different trig functions. Cosine over sine is cotan x, and cosine x is cosine x. And so now I'm done. Here I used the quotient identity. So I've just got one more example, but it uses all the same strategies we've already used. You've noticed that Pythagorean identity comes up a lot, multiplying things out, getting a common denominator. This just uses the same strategy. So if you feel comfortable, you can skip this last example. We'll run through it pretty quickly anyway. So the grand finale. We've got two different terms, and we're supposed to try to combine it into just 2 secant x. So clearly this one is the more complicated, and I need to get a common denominator. So the first thing I'll do is multiply this one on top and bottom by 1 plus sine squared x, so I can get that in the denominator of this term. So I get 1 plus sine theta on top and bottom times 1 plus sine theta. And now I'll have 1 plus sine theta cosine theta on the bottom. This one I need to multiply on top and bottom by cosine theta. So I get cos squared theta over 1 plus sine theta times cos theta. And the strategy here is common denominator. Now if I FOIL this out, I'm going to end up with 1 plus 2 sine theta plus sine squared theta, and here I have plus cosine squared theta all over this denominator, which I'll leave factored because it doesn't seem like multiplying that out would help me very much. There's no identity that's going to help me out there. So that's FOIL. Now if you look at sine squared plus cosine squared, that equals 1. So I have 1 plus 1 is 2 plus 2 sine theta over this denominator. That's by Pythagorean identity. Now notice I have a 2 in both of these terms, but I don't have a 2 down here. So let's factor that out. So this is by factoring. Then I have a 1 plus sine theta on top and bottom. So let's see, where do I have space for this? Let's take it up here. I end up with 2 cosine theta by simplifying. And notice 1 over cosine theta is the same as secant, so then I multiply that by 2, and I get 2 secant theta by the reciprocal. And I'm done. So I know that these proofs of identities are a little bit tricky, but I promise you will get better at them. We'll do tons of practice in class, and these examples that we just went over should just serve as a guide and give you some ideas for how you play around with this sort of thing. So good luck, and let's keep working on this.